तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we continue our discussion on dynamic programming. We continue to solve examples where the decision variables take continuous values. In the previous example, we had a linear objective function with nonlinear constraints and the variables were continuous. In this example, we will have a nonlinear or a polynomial objective function subject to a linear inequality as a constraint. The objective function is to minimize z equal to x1 cubed minus 5x1 square plus 8x1 plus x2 cubed minus 2x2 square minus 10x2 plus 10, subject to x1 plus x2 less than or equal to 4, x1 x2 continuous and greater than or equal to 0. As usual, we define the stage, state, decision variable and criterion of effectiveness. We have two variables here, so we solve in two stages and each variable represents a stage. The state is the resource available for allocation. The constraint x1 plus x2 less than or equal to 4 does not tell us what the resource is, therefore we generally define it as resource available for allocation. Decision variables of course are the values of the variables x1 and x2, and the criterion of effectiveness is to minimize the objective function z given by x1 cubed minus 5x1 square plus 8x1 plus x2 cubed minus 2x2 square minus 10x2 plus 10. We have two variables. In this problem or in our approach, we are going to first solve for variable x1 and then for variable x2. We may call it a kind of a forward recursion. Alternately, we can also rewrite the objective function such that the objective function is x2 cubed minus 2x2 square minus 10x2 plus 10 plus x1 cubed minus 5x1 square plus 8x1. We will later see why we decided to rewrite the objective function. Now, because we have rewritten the objective function this way, it makes it easier for us to solve for variable x1 first and then for variable x2. The constant now is added along with the x2 terms and not along with the x1 terms. So, as usual, n equal to 1, one more stage to go. f1 of s1 comma x1 is equal to x1 cubed minus 5x1 square plus 8x1. f1 star of s1 is the best value of x1 that optimizes the function f1 of s1 x1. Minimize x1 cubed minus 5x1 square plus 8x1 subject to the condition 0 less than or equal to x1 less than or equal to s1. Differentiating with respect to x1 and setting it to 0, we get 3x1 square minus 10x1 plus 8 equal to 0, which would give us x1 equal to 2 or x1 equal to 4 by 3. Now we have two values of x1, which is x1 equal to 2 and x1 equal to 4 by 3. We also observe that when we solved for 3x1 square minus 10x1 plus 8 equal to 0, we can easily solve for x1 by factorizing it. Minus 10x1 can be written as minus 6x1 minus 4x1, from which we would get x1 equal to 2 or x1 equal to 4 by 3. Now, in order to find out which one is the minimum, we now have to find out the second derivative. So, second derivative would be 6x1 minus 10. Now, we substitute the two values that we have got, that is x1 equal to 4 by 3 and x1 equal to 2. When we substitute x1 equal to 4 by 3 in 6x1 minus 10, we get minus 2, which indicates that 4 by 3 is a local maximum. When x1 equal to 2, the value is plus 2, indicating that x1 equal to 2 is a minimum. Now, if we go back to the function is x1 cubed minus 5x1 square plus 8x1, it is a cubic in x1. So, we also have to find out in the range 0 x1 to 4, we also have to find out the value of the function at the end points. Unlike a quadratic, in a cubic we need to find out the value at the end points. So, when we find the values at the extreme points, at x1 equal to 0, the value of the function is 0, and at x1 equal to 4, it is 16. Now, if we compare the value at x1 equal to 0 and x1 equal to 2, we observe that the minimum actually happens at x1 star equal to 0. So, the minimum happens at x1 star equal to 0 and f1 star of s1 is equal to 0. We also explain this using this figure. This is a kind of a freehand diagram of the polynomial that we have, and we observe that the two values that we obtained are x1 equal to 2 here and x1 equal to 4 by 3. x1 equal to 4 by 3 represents a local maximum, x1 equal to 2 represents a local minimum, x1 equal to 0 is here and x1 equal to 4 is here farther. We also realize that for values less than 4 by 3, it is decreasing and it is at 0 at x1 equal to 0, while for values greater than 2 it will be increasing. So, the minimum happens to be at x1 equal to 0 with f1 star of s1 equal to 0. Continuing with n equal to 2 and 2 more stages to go, f2 of s2 comma x2 is equal to x2 cubed minus 2x2 square minus 10x2 plus 10 plus f1 star of s2 minus x2. Now, this comes, f1 star of s2 minus x2 comes because we assume that there is an s2 of resource available, out of which an x2, a value x2 is allocated to variable x2, and the balance s2 minus x2 goes as s1 for allocation to variable x1. Now, f2 star of s2 is the value of x2 that minimizes x2 cubed minus 2x2 square minus 10x2 plus 10 plus 0. The 0 comes because of f1 star of s2 minus x2. We have already seen here that f1 star of s1 is 0, therefore, f1 star of s2 minus x2 is also 0. Now, in the range 0 less than or equal to x2 less than or equal to 4. The 4 comes from the inequality here. 4 is the amount of resource available at the beginning. So, S2 takes value equal to 4. So, x2 is between 0 and 4. Once again we have to differentiate with respect to the variable x2 and we equate it to 0. We get 3x2 square minus 4x2 minus 10 equal to 0, that comes from the first 3 terms. The terms x2 cubed minus 2x2 square minus 10x2 on differentiation would give us 3x2 square minus 4x2 minus 10 equal to 0. Now, this is a quadratic equation and we have to solve for x2. So, we do not factorize it. So, we use the formula minus b plus or minus root of b square minus 4ac by 2a to get x2 is equal to 4 plus or minus root of 136 by 6. we also have, so we get two values, one is 4 plus root 136 by 6 and the other is 4 minus root 136 by 6. Now we do not consider the negative value because x2 should be greater than or equal to 0. So we consider only the positive value or the positive root, and we have x2 is equal to 2.6103. Now we have to find out whether this is a minimum, and to do that we further differentiate or we find out the second derivative. Second derivative on differentiating this would give us 6x2 minus 4. So 6x2 minus 4 at 2.6103 gives us a positive value of 11.66 at x2 is equal to 2.6103. Therefore, the optimum is x2 star is equal to 2.61 and f2 star of 4 or the objective function value is minus 11.9446. This we obtain by substituting 2.6103 in this expression, x2 cubed minus 2 x2 square minus 10 x2 plus 10. So when we substitute x2 equal to 2.6103, we get the value of the function as minus 11.9446. x1 star is already 0, therefore the best values are x1 star is 0, x2 star is 2.61 or 6103 and f2 star of 4 or the minimum value is minus 11.9446. Now there are a couple of things that we did in this example. In this example we decided to choose variable x1 first and then we chose variable x2. If we look at the function carefully, normally in a backward recursive mode we would have solved for variable x2 first and then at n equal to 2 we would have solved for x1. But then here we did something, we rewrote the objective function or rearranged the terms. The x2 terms were grouped together first and then the x1 terms were written so that we could optimize x1 first. The reason was very simple. When we had the first derivative here, we could factorize it to get 2 or 4 by 3. If we had used x2 first, we would be forced to use the quadratic or the roots of the quadratic equation and we would have ended up getting decimals. So wherever we observe that it is possible to factorize and get round values or good values, we can use that variable as the first variable to optimize, which is what we did here. One should also understand that if we had worked out this problem the normal way by choosing variable x2 in the first stage or at n equal to 1 and then choosing variable x1 at n equal to 2, we should and we would have got the same answer. The optimal solution in this problem is x1 star is equal to 0, x2 star is equal to 2.61 and the value is minus 11.9446. The other difference between the earlier problem and this problem, we need to look at that. In this problem, our constraint is an inequality, x1 plus x2 is less than or equal to 4, whereas in the earlier problem the constraint was an equation. So whenever the constraint is an equation at n equal to 1 more stage to go, we did not optimize or we did not differentiate in the earlier problem. We substituted the value s1 because of the equation all the resource s1 will have to be utilized. When we have an inequality, as in this case, it is not absolutely necessary for us to use the entire resource s1 that is available. Here we have a resource s1 that is available. It is not absolutely necessary for us to use all the resource s1 available. When we have an inequality, we differentiate or we optimize at the first stage and then we got two values and it happened in this example that x1 equal to 0 was the actual optimal. Another important thing from this problem is, because this function is cubic and as explained in this figure, it is not enough for us to restrict ourselves to the minimum and maximum found by the differentiation. It can happen, as in this example, the extreme point or the end point x1 equal to 0 is actually the minimum, while the local minimum x1 equal to 2 gave a higher value of the objective function. Now this is possible for higher order functions, whereas if it were a quadratic, it would have been enough because the quadratic would have only one optimum. Moment we have cubic and higher order functions, one need to look at what value the function takes at the end points or the extreme points. So these are the things that we have learned using this example. So in this example we have tried to minimize a cubic function subject to an inequality. The most important thing is, when we have an inequality, we do not substitute the value of the state variable. Instead we optimize at the first stage, or we optimize at n equal to 1. This is the most important thing that we learn from this example. Let us continue our discussion with one more example, which is shown here. The problem is to maximize 2x1 plus 3x2 plus x1 x2. Now what is different in this objective function compared to the previous objective functions in the last two examples are that we have a product form x1 x2 appearing in the objective function here. In example 4, when we first introduced continuous variables, we did have a product form in the constraint, but the difference here is there is a separate x1 term, there is a separate x2 term, and then there is a product term x1 x2. Now with this kind of an objective function, or with this type of terms, it may be difficult for us at the moment to identify the objective function and separate it with respect to each stage. Now we will see how we handle this kind of peculiarity as we go on with this example. We again have a constraint of the type x1 plus x2 is less than or equal to 2 and x1 comma x2 greater than or equal to 0. We once again define stage, state, decision variable and criterion of effectiveness. Again we have two variables, so we solve it in two stages. So the two variables x1 and x2 give us the two stages. There are two stages and each stage corresponds to each variable. State once again is defined in a very general way as resources available for allocation. We do not know what this 2 represents, so we call it a resource, and the amount of resource available for allocation is the state variable. The decision variables are the values of x1 and x2, which we are going to find out. The criterion of effectiveness or the objective function is to maximize z. Z is given by 2x1 plus 3x2 plus x1 x2. Once again in this example, the term x1 x2, the product term which is present in the objective function, makes it difficult to separate the objective function in terms of two separate functions of the variables. Now to overcome this, what we do is we try to factorize the objective function in this case. Now 2x1 plus 3x2 plus x1 x2, what we can do is we can add a 6 and subtract a 6 from this. So if we have 2x1 plus 3x2 plus x1 x2 plus 6 minus 6, and we take only these three terms and a plus 6, and we realize that we can factorize it, and on factorization we will get x1 plus 3 into x2 plus 2 minus 6, or if we expand this x1 plus 3 into x2 plus 2 minus 6, we would get x1 x2 plus 2x1 plus 3x2 plus 6 minus 6, which is 2x1 plus 3x2 plus x1 x2, which is what our original objective function is. So we factorize this and we get an objective function which is in this form, x1 plus 3 into x2 plus 2 minus 6. We can always leave out a constant from any objective function. So we write the problem as to maximize x1 plus 3 into x2 plus 2, subject to x1 plus x2 less than or equal to 2, x1 x2 greater than or equal to 0. We have left out this minus 6, therefore in the end we have to add a plus 6 to the objective function. So at the moment we leave it out. Now this is a form with which we are quite comfortable, because we have two variables x1, x2, the constraint is of the form x1 plus x2 less than or equal to 2, the objective function is clearly product of two terms, one involving only x1 and constant and the other involving only x2 and constant. So now we can nicely do it the way we are comfortable with, and we continue to solve this problem. So when n equal to 1, one more stage to go, we try to optimize on the variable x2 first. So we have f1 of s1 comma x2 is equal to x2 plus 2. We take only this term, the x2 plus 2 term. f1 star of s1, best value of this function, is to maximize x2 plus 2 subject to the condition 0 less than or equal to x2 less than or equal to s1. We assume that a resource s1 is available here for variable x2, which means something has been allocated to x1 and the balance is available as s1. So subject to 0 less than or equal to x2 less than or equal to s1. Now here again we optimize it, and it turns out that the optimum value is at x2 star equal to s1, because we are maximizing x2 plus 2 and x2 has an upper limit of s1. So obviously the best value of x2 is going to be s1. Because of the presence of the inequality here, we optimized it. We optimize this function subject to 0 less than equal to x2 less than or equal to s1. The maximum value is got at x2 star equal to s1, and f1 star of s1 is equal to s1 plus 2. Now we go to the second stage, or n equal to 2, two more stages to go. f2 of 2 comma x1, 2 comes from this. So 2 comma x1 is x1 plus 3 into f1 star of 2 minus x1. 2 minus x1 again comes because out of this available 2, there is an x1 greater than or equal to 0 which is allocated to variable x1. So 2 minus x1 greater than or equal to 0 is now available as s1 for allocation for variable x2. So here again we are aware that s1 is greater than or equal to 0. Now this s1 is greater than or equal to 0 because if you go back here, both x1 and x2 have to be greater than or equal to 0. So if we give an allocation x1 greater than or equal to 0 and less than or equal to 2, so the balance s1 will have to be greater than or equal to 0. So 0 less than or equal to x2 less than or equal to s1 is applicable here. Similarly 0 less than or equal to x1 less than or equal to 2 is applicable here. So this would mean f2 star of s1 is to maximize x1 plus 3 into f1 star of 2 minus x1. We also know that f1 star of a given s1 is s1 plus 2. So f1 star of 2 minus x1 will be 2 minus x1 plus 2, subject to 0 less than or equal to x1 less than or equal to 2. So maximize x1 plus 3 into 4 minus x1 subject to 0 less than or equal to x1 less than or equal to 2. This on multiplication would give us minus x1 square plus x1 plus 12. First derivative equal to 0, we get x1 equal to half. Now that comes because we have minus 2x1 plus 1 equal to 0 gives us x1 equal to half, and the second derivative will be minus 2 indicating which is negative and indicates a maximum. So we are interested in maximizing it. Therefore we have x1 star equal to half. Now if x1 star is equal to half, s1 equal to 3 by 2. That comes because because x1 star is equal to half. So, we have used up half here. So, a 3 by 2 is now available as S1 for allocation of variable x2. We also know that x2 star is equal to S1, therefore, the 3 by 2 that is available for allocation goes to variable x2. So, x1 star is half, x2 star is 3 by 2. The value of the objective function at present is 49 by 4, that is the value of the function minus x1 square plus x1 plus 12 at x1 equal to half is 49 by 4, but then we also have to subtract a 6 because when we factorized, the original objective function turned out to be x1 plus 3 plus x2 plus 2 minus 6. We left out this minus 6 and we included only this, and therefore we have to include that minus 6 here. So, we subtract a 6 from the z to get 25 by 4 for the original problem. Now, the most important thing in this is when we have an objective function of this type, where this is the first time we have considered an objective function which has x1 terms, x2 terms and a product term. Now, the presence of the product term along with the x1 terms and the x2 terms makes it difficult. Therefore, factorization came to our rescue. Now, if the function is such that we can factorize it, then we have to use it to our advantage and then convert the objective function into this form where we can separate the x1 terms and the x2 terms. In this case, it turned out to be a product of a function of x1 and a function of x2. If we had started with this, then it would have become very difficult. We either end up trying to optimize for two variables in one stage, or we end up having to identify different types of state variables. So, we avoid or overcome that difficulty by factorizing and by bringing it into this product form, so that we can separately take out the x1 term as well as the x2 term, and then we can separately optimize for each one of them. So, it is important that when we have these kind of objective functions, we should explore possibilities by which we can convert them into the form f1 of x1 plus f2 of x2, or f1 of x1 into f2 of x2. In this case, it was the product form that we used. Also, we need to understand that whenever we have an inequality coming in, we do not substitute, we need to optimize. In this case, we did optimize, maximize x2 plus 2 subject to 0 less than equal to x2 less than equal to s1. It turned out that the value of x2 star was the available resource, but then we did optimize to find out that the maximum value happens at x2 star is equal to s1. So, couple of things that we could learn from this example is that when we have an objective function of this form, then we could use factorization to convert it into a form with which we are familiar and comfortable. And the second point is, if we have an inequality, then we need to optimize at n equal to 1 stage. We continue our discussion in dynamic programming through another example from which we would learn a few new things. Now, this problem is a typical manpower planning problem. So, the problem is as follows. Manpower requirements for a company for the next 4 months are 90, 120, 80 and 100 respectively. They can employ more than the requirement in any month, but if they do so, they incur a cost of underutilization. Now, this cost of underutilization is 10 times x, where x is the additional number of employees over and above the minimum required. For example, the minimum required in the first month is 90. If they end up employing 95 people, then the additional, because of the additional 5, they would incur an underutilization cost of 10 into 5, which is 50. They cannot employ less than the minimum required. So, they can only employ 90 or more for the first month. They cannot employ fewer than the requirement. Now, there is also a cost of changeover given by y square, where y is the amount of decrease or increase of the employees. For example, if they choose to employ 95 people for the first month instead of a minimum 90, and say 120 they employ in the second month, then there is a difference of 15 from 95 to 120. Remember, 90 is the requirement, and if they employ 95, then from this 95 to 120 there is a changeover cost, an increase cost. So, the cost will be 15 square, which is 225. Similarly, if they choose to employ 100 here, then there is a decrease of 20. So, that would result again in a changeover cost of 20 square, which is 400. So, whether there is an increase or there is a decrease, there is a changeover cost given by y square, where y is the amount or the extent of decrease or increase of the employees. Initially 100 employees are available. So, 100 employees are available here at the beginning of the first month. Now, find out the least cost solution to employ people in the 4 months. So, this problem we will now look at. Now, we define stage, state, decision variable and criterion of effectiveness for this. Now, there are 4 months. So, each month would act as a stage. So, we have 4 stages, n equal to 1 to n equal to 4, which are represented by the 4 months. State in this example is the number of employees available in the month, or the number of employees who have been employed in the previous month. Now, for example, when we look at the beginning of the first month, now 100 employees are available in the beginning of the first month. So, that is the state variable. Now, if we look at the beginning of the second month, then the number of people who are employed in the first month would now be available at the beginning of the second month, and therefore, that would be the state variable. So, state variable here is the number of employees available at the beginning of the month, which is the number of employees who were employed in the previous month. Decision variable is x1 to x4, which is the number of people to be employed in the current month or in this month. So, we define x1 to x4 for months 1 to 4. Criterion of effectiveness or the objective function in this example would be to minimize the sum of the changeover cost and the underutilization cost. There are 2 costs. There is a changeover cost, there is an underutilization cost. So, we want to minimize the sum of these 2 costs as the minimum total cost. We use a backward recursive approach. So, when n is equal to 1 more stage to go or 1 more month to go, we are effectively looking at the 4th month. So, because of the backward recursion, when we have 1 more month to go, we are here. So, we are looking at the 4th month, we assume that we are at the end of the 3rd month. So, f1 of s1 x4, s1 is the state variable, which is the amount of people available at the beginning of the 4th month, which is also the number of people employed in the 3rd month. We will see that later. So, number of people available at the beginning of the 4th month is s1. x4 is the decision variable, which is the number of people who are going to be employed in the 4th month. The requirement for the 4th month is 100. So, number of people who are going to be employed in the 4th month will have to be more than 100. So, if it is more than 100, then x4 minus 100 is the excess number of employees who contribute to the underutilization cost. So, the underutilization cost is 10 times x4 minus 100. Now, there is a changeover from x3 to x4, because x3 is the number of people employed in month 3, x4 is the number of people employed in month 4. So, x3 minus x4 is the changeover. Now, x3 is the same as s1. The state variable is the same as the number of people employed in the previous month. So, we have S1 minus X4 the whole square. This is the changeover cost. So, the objective function is the sum of the underutilization cost and the changeover cost. Now, F1 star of S1 is the best value of X4, which is to minimize the sum of the underutilization cost and the changeover cost to minimize 10 times X4 minus 100 plus S1 minus X4 the whole square, subject to the condition X4 is greater than or equal to 100. Company should employ at least the minimum number or more and cannot employ less than 100 in this case. So, once again differentiating with respect to X4 and equating to 0, we would get 10 minus 2 times S1 minus X4 is equal to 0. So, that comes from this expression. This would give us 10, this would give us 2 times or minus 2 times S1 into X4 equal to 0, from which X4 star is equal to S1 minus 5. Now, we also have to find out the second derivative and show that the second derivative is positive, which would indicate a minimum, which we can see from here. The minus 2 into minus X4 would give us a plus 2 X4, which would give us a minimum. So, X4 star is equal to S1 minus 5 in this case. Now, we also have two cases coming in here, because since X4 is greater than or equal to 100, we need to have a couple of things. When S1 is greater than or equal to 105, then X4 star will become S1 minus 5. For example, if S1 were 110, then the best value of X4 star would be 110 minus 5. On the other hand, if S1 was 100 itself, then S1 minus 5 is going to give us 95, which is going to violate X4 greater than or equal to 100. So, in such a case, X4 star will take a value 100. So, X4 star will take values depending on what the value of S1 is. So, if S1 is greater than or equal to 105, then X4 star will be S1 minus 5, and F1 star of S1 will be 10 times S1 minus 105 plus 25. This comes because when we substitute X4 is equal to S1 minus 5, becomes 10 into S1 minus 5 minus 100, which is 10 into S1 minus 105, and if X4 is S1 minus 5, then S1 and S1 will cancel out each other and we would get a 25. So, when X4 star is equal to S1 minus 5, F1 star of S1 is 10 times S1 minus 105 plus 25. Now, if S1 is less than 105, then S1 minus 5 will become less than 100, but then which will violate this condition. So, X4 star will take a value 100. So, X4 star takes a value 100 when S1 is less than 105, and substituting here, the underutilization cost will become 0, only the changeover cost will be there, and F1 star of S1 will become S1 minus 100 the whole square. Now, n equal to 2, 2 more stages to go, F2 of S2 x3. Now, when we have 2 more stages to go, we are actually here. We assume that we are in the beginning of month 3 and we have a certain number of resources available to us, which is the number of people who worked in month 2. So, when we are here, when we have n is equal to 2, 2 more stages to go, we are here and we have to make a decision for variable x3, assuming that S2 people are available, and that is what we write here. So, F2 of S2 comma x3, 10 times x3 minus 80, 80 comes as the minimum requirement for month 3, minimum requirement for month 3 is 80. So, we have x3 minus 80 plus S2 minus x3 the whole square represents the changeover. So, there is an S2 available at the beginning, x3 is employed. So, S2 minus x3 the whole square represents the changeover plus F1 star of x3. F1 star of x3 comes in because the number that we employ this month x3 is now available at the beginning of the next month as S1. So, the function is 10 into x3 minus 80 plus S2 minus x3 the whole square plus F1 star of x3. F2 star of S2 is to minimize 10 into x3 minus 80 plus S2 minus x3 the whole square plus F1 star of x3 subject to the condition x3 greater than or equal to 80. Now, we go back to the problem and we observe that the 4 requirements are 90, 120, 80 and 100. One look at these numbers is going to tell us that for the second month it is not advisable to have more than 120 people at all, because if we have more than 120 people, then we are going to unnecessarily have an underutilization cost somewhere here, and the changeover cost is going to be more because the next month's requirement is between 80 and requirement is 80, and therefore the cost of changeover is also going to increase. So, one look at the data would tell us that for month 2 we are going to employ only 120 people. We use this information in this problem to simplify this problem further. So, we go back here. So, in this problem the maximum requirement is for the second month, and having x2 star greater than 120 would only increase both the underutilization cost as well as the changeover cost. So, we will have x2 star is equal to 120 and S2 is going to be 120 in this case. So, we can comfortably substitute for S2 equal to 120 in this. Now, we also have 2 functions for F1 star of S1. See, in this case we have 2 functions for F1 star of S1. F1 star of S1 took 10 into S1 minus 105 plus 25 in a certain range, and F1 star of S1 took S1 minus 100 the whole square in a different range where S1 is less than 105. Now, we have to substitute both these expressions here. So, we have 2 expressions for F2 star of S2. Now, what we do here is, here we understood that S2 is 120 because x2 star is 120. So, we are going to substitute S2 equal to 120, and we are also going to substitute the 2 expressions for F1 star of x3. F1 star of x3 is the same as F1 star of S1. So, we substitute both these expressions. So, the first one would be F2 star of S2 is to minimize 10 times x3 minus 80 plus 120 minus x3 the whole square plus 10 into x3 minus 105 plus 25. So, we have used the first expression here, 10 into S1 minus 105 plus 25, but that is within the range greater than or equal to S1 greater than or equal to 105. Now, this implies x3 greater than or equal to 105, and x3 has to be less than or equal to 120 because that is the maximum. Therefore, in the range of x3 between 105 and 120, we have this function which minimizes 10 times x3 minus 80 plus 120 minus x3 the whole square plus 10 times x3 minus 105 plus 25. On the other hand, in the range x3 less than 105, let us go back. Now, when S1 is less than 105, F1 star of S1 is S1 minus 100 the whole square. Now, S1 is the same as x3. So, in the range x3 less than 105 or in the range of x3 between 80 and 105. 80 comes from the fact that the minimum requirement is 80. So, in the range 80 to 105 that we have here, now the function becomes minimize 10 into x3 minus 80 plus 120 minus x3 the whole square plus x3 minus 100 the whole square. This x3 minus 100 the whole square comes from S1 minus 100 the whole square. So, we have written both these functions for F2 star of S2 depending on the range of values of x3. So, if x3 is in this range, we have one function, x3 is in the other range, we have another function. So, we have to separately optimize both these functions and find out what is the minimum value of x3. Now, to do that, we differentiate the first expression with respect to x3 and we equate it to 0. So, this would give us a 10, this would give us 2 times 120 minus x3 into minus 1, this would give us another 10. So, we get 10 minus 2 times 120 minus x3 plus 10 equal to 0, from which x3 star is equal to 110. Second derivative is positive because we have a plus 2 x3 term, that would give us a plus 2 which is positive at x3 equal to 110, and therefore the value of x3 star is equal to 110 is indeed a minimum. We also need to check that the x3 for this function should be within the range 105 to 120, and it happens that 110 is within the range, so we do not have to worry. If x3 star had exceeded 120 or were less than equal to 105, then we have to go back and substitute at the extreme points to find out which one is the minimum. Now, in this case it turned out that the optimum, which is 110, happens to be in the range, and therefore we comfortably use this 110. Substituting, we would get f2 star of 120 equal to 475. We go back and substitute here, this would give us a 400, this would give us a 0, this would give us a 110, 5 into 10, 50, so this would give us another 25, so put together we would get 475. Now, we go to the other expression. Now, we have to differentiate this to get a value of x3, also keeping in mind the range. So, when we do that, this would give us a 10, this would give us a minus 2 times 120 minus x3, and this would give another 2 times x3 minus 100. So, that is what we get here, 10 minus 2 times 120 minus x3 plus 2 times x3 minus 100 equal to 0, from which x3 star is 107.5. Second derivative is positive because there is a 2x3 here and a 2x3 here. So, 4x3 it will be plus 4 and it is positive. But we need to look at something else. The value is 107.5 here, but then we know that it is valid between 80 and 105. So, the optimum exceeds the range. So, we need to go back and substitute whether it is minimum at 80 or whether it is minimum at 105. Because this function is quadratic and because at 107.5 it is a minimum. So, we observe that within this range the value at 105 will be smaller than the value at 80. So, x3 star is actually 105 in this case and not 107.5. So, we will take 105. So, x3 star will be 105, and when we substitute, f2 star of 120 is 487.5. So, in this case the optimum value of x3 star is 110, which is the best value corresponding to the lower of these two. So, lower of 475 and 487.5. So, f2 star of 120 is 475 with x3 star equal to 110. Now, we proceed again at n equal to 3 more stages to go, which means we are somewhere here. We are here at the beginning of the second month and we have a state variable and a decision variable to make. So, at n equal to 3 more stages to go. f3 of s3, assuming s3 is the state variable and x2 is the decision variable, 10 times x2 minus 120, 120 is a minimum requirement, x2 is what we are going to employ for month 2, plus s3 minus x2 the whole square, this represents the changeover cost, plus f2 star of x2. Now, f3 star of s3, which is the best value of this function, is given by an x2 such that it minimizes 10 times x2 minus 120 plus s3 minus x2 the whole square plus f2 star of x2. This f2 star of x2 comes in because whatever we have as x2 in this month will be available as S2 in the beginning of the next month, subject to the condition the minimum x2 greater than or equal to 120 is also satisfied. Now we have already seen here that because of the nature of these 4 values 90, 120, 80 and 100, we have already seen that it is not advisable to have more than 120 employed in the second month, and therefore we have already seen that x2 star is equal to 120. So all we need to do here is to show or is to take the value x2 star is equal to 120, which we know. So in this case x2 star is going to be 120. So we are not going to optimize this and find out that x2 star is 120. We may do that. At the same time, since we know that 120 is the maximum and we have already used this in the earlier result, we have x2 star is equal to 120 and f3 star of S3 will be S3 minus 120 the whole square plus 475. When x2 star is equal to 120, the underutilization cost is not there. There is no underutilization because we are not employing more people. Only the changeover cost is there. So whatever is available as state variable S3, from that S3 we are going to bring it to 120. So you get S3 minus 120 the whole square plus F2 star of x2 has been found out to be 475. So we add this 475 to get F3 star of S3 is equal to S3 minus 120 the whole square plus 475. Now we go to the last one, n equal to 4, 4 more stages to go, which means we are at the beginning of the problem, which means we are at the beginning of month 1. Month 1 minimum requirement is 90, people available at the beginning of the planning period or available at the beginning of month 1 is 100. So we go back to n equal to 4, f4 of 100 comma x1. This 100 comes in because 100 is the amount of people available at the beginning of the first month and x1 is the decision. X1 is the number of people that we are going to employ in the first month. So f4 of 100 comma x1 is 10 times x1 minus 90. 90 is the minimum requirement for month 1. So if we end up employing more than x1, then there will more than 90, there will be an x1 minus 90 which will add to the underutilization cost, and whatever be the value of x1 from 100 we are bringing it to x1. So there is going to be a changeover cost. So 100 minus x1 the whole square represents the changeover cost plus f3 star of x1. f3 star of x1 comes because this x1 is available as S2 at the beginning of the stage n equal to 3. So this x1 is going to go as S2. So earlier we have defined f3 star of S3. So now this x1 is going to go as S3. So we write f3 star of x1. Now f4 star of 100 is the best value that this function can take for a given state variable which has a value 100, and that would minimize this function, minimize 10 times x1 minus 90 plus 100 minus x1 the whole square plus x1 minus 120 the whole square plus 475. The x1 minus 120 the whole square plus 475 comes from the earlier statement S3 minus 120 the whole square plus 475. So the whole thing repeats again. Most importantly, subject to the condition x1 less than greater than or equal to 90. Now this 90 is the minimum requirement that we have for this. Now once again differentiating with respect to x1 and equating it to 0, we get this expression would give us a 10, this would give us 2 times 100 minus x1 into minus 1, and this would give us 2 times x1 minus 120, constant does not yield anything. So we get 10 minus 2 times 100 minus x1 plus 2 times x1 minus 120 equal to 0, from which x1 star is equal to 107.5. second derivative would be positive because this is a 4x1 term, this is another, this is a 2x1 term, this is a 2x1 term. So together we have 4x1. So second derivative will be 4 and it is positive, therefore 107.5 is a minimum. Now it also satisfies the condition x1 greater than or equal to 90 and therefore we are comfortable, and it is also less than 120, which is one of the assumptions that we had made. So it also satisfies that and therefore does not give us any trouble or any difficulty. We can comfortably assume the value 107.5. Now this is within the range, and F4 star of 100 will now on substitution give us 107.5 minus 90 is 17.5 multiplied by 10 would give us 175. 100 minus 107.5 is 7.5 square is 56.25. 107.5 minus 120 is 12.5, square is 156.25 plus 475 gives us 862.5 as the cost. Now the optimum solution is x1 star is equal to 107.5 that we found out now, x2 star is 120 which we assumed in this problem, x3 star was 110 that we found out, x4 star was 105 which we also found out right at the beginning, because when x3 star is 110 we go back here at n equal to 1, when x3 star is 110 which implies that S1 is 110. So S1 is greater than 105, therefore x4 star will be S1 minus 5 and it will become 105, and the value of the objective function is 862.5. There are a few other things. We realize that x1 star is not an integer, though it represents the number of people employed. Now in the problem, if we go back to the original problem does not explicitly state that the decision variables are integers, therefore we ignored it and we solved it as a continuous variable. Due to the quadratic nature of the objective function, we can actually evaluate x1 star equal to 107 and x1 star equal to 108 and find out actually both give the same value of the objective function. We can actually choose either of them. This problem was made much simpler by the fact that the maximum demand occurs at the second period, making x2 star equal to 120. Now this considerably decreases the computational effort, and we have used this to our advantage while solving this problem. So a quick summary of this problem had a quadratic kind of an objective function. It also gave us situations where, as in this stage, the function f1 takes two different values depending on the range of the variables, in which case we have to carry it forward to the next stage and then we need to solve them. We continue our discussion in the next class with more examples.